Good morning, fifth graders. Today you'll be doing lesson 4.4 in filling and wrapping in your homerooms. I am at the Math Olympiad tournament, so please do your best to be respectful of the students learning around you. We'll start by correcting the homework. Remember, you can pause at any time if you need to look at something more closely. Number 3, these are approximations because we use 3.14 for pi and they are using the pi button. So 3a, it should be around 28.3 centimeters cubed. 3b should be 20 layers, and 3c should be 565 centimeters cubed, approximately. Number 4, the surface area would be 674 centimeters squared, and the volume is 1,327 centimeters cubed. 4 is 1,037 centimeters. That's 5. Surface area 1,037 centimeters cubed, and volume 2,042 centimeters cubed. I think I said cubed twice. Surface area is squared. Number 6, A, the pipeline, 1 kilometer of pipeline would hold about 3,141.6 meters cubed of oil. And a 5,000 kilometer pipeline would hold 15,708,000 meters cubed of oil. It's a lot of oil. Number 7 is you had the scale model, so you needed to find the volume. The volume would be about 170 centimeters cubed. The surface area would be about 170 centimeters squared. Number 29, the packages. What package has the greater surface area? The rectangular, which was 1,128, and the cylinder was 911 centimeters squared. So the prism was greater. Which package had a greater volume? That would be the rectangular prism as well. It had a volume of 2,016 centimeters cubed, and the cylinder was only 1,884 approximate centimeters cubed. Number 38, these are all related to how the scale factor affects the volume. The scale factor will always be this, the volume will always be the scale factor cubed. So 2 cubed is 8. B, 3.5 cubed is 42.875, and then C, the scale factor is F, so it would be F cubed. Number 47 asked how you could estimate. You didn't have to find an exact answer, but they had 2 strategies. One way would be to find the volume of the large circle and the volume of the small circle, and then use the average. The other strategy they said was to average the radii, and that is not as accurate or is not equivalent to the other. Some of you may also have found both and subtracted maybe. Anyway, just looking at how you are able to problem solve and estimate. So in today's lesson, it is 4.4, we're going to talk about cones and spheres. We're skipping the demonstration. I'm going to show you a tool online that you can use. It's proving why the 2 formulas work. So cylinders are not the only important solid figure with curved edges and faces. Balls in the shape of spheres play an important role in many popular sports. Cones are used to serve ice cream and direct traffic around construction zones. The size and shape of any sphere depends on the size of the radius, which is the distance from any point on the surface to its center. You can see that here. We can describe any sphere using this single dimension. So you only need the radius in order to find the sphere. Volume and surface area. And then the cone depends on the size of 2 dimensions, the height of the cone, and the radius of the circle base. In this problem, you'll develop strategies for calculating volumes of spheres and cones and see how changes in their dimension cause changes in their volumes. It's hard to measure the volume of a sphere or cone by filling it up with an exact number of unit cubes because unit cubes are square, so they don't fit very well in curved shapes. Fortunately, there is a helpful relationship among the volumes of cylinders, spheres, and cones. A simple experiment will reveal the relationship and the formulas for the volumes of spheres and cones. In this problem, you'll make a sphere, a cone, and a cylinder, each with the same diameter and same height. So here's where I'm going to show you a tool online to use, this is located on the filling and wrapping. It's called the pouring and filling tool, and all of these have the same radius. It says right here the diameter is the same for the sphere, the cone, and the cylinder, so that's why we can use this. I fill up my sphere with water, and then I can pour it into the cylinder. And what do you notice about the relationship, about how much of the sphere is filled? How much of the cylinder is filled by the water from the sphere? I can do it again to show you, see if you can come up with an idea. Without being able to measure, it's hard to estimate, but it is about 2/3. 2/3 the volume of the cylinder is filled by the sphere. And the same thing with the cone. You can make a prediction now. The cone will fill, how much do you think? If you look at the relationship between what we saw with the sphere, the cone fills 1/3 of the area, the volume of the cylinder. So using that information, we'll come back here and talk. Using the results of experimenting with the sphere to find the volume of the cylinder and the volume of the original sphere. So if we had numbers to go with that, you could test it out. And let's say we wanted to do, where's my pen? We had a radius of 5. If you have a radius of 5, you can use your volume of a cylinder to find pi r squared times the height, right? And we'll call the height 8. Okay, so then you would plug in your numbers. For r squared is 25. So 3.14 times 25 is 78.5 times the height is 628. 628 would be the volume of our, we'll call them centimeters, cylinder. Okay, and if I had the sphere with the same radius, how would I find the volume? It was 2/3 of pi r squared times height. Now, if you plug in, you should get that would be 418 2/3 approximately, because I'm just using 0.66666 for my 2/3. That is our volume of the sphere. Now, you can combine like terms on some of these and know that the height of the sphere is also known as the diameter, right? Or 2 times the radius. So when we combine like terms, I'm not going to call it the diameter, I'm going to call it 2 times the radius, right? 2 times the radius is equal to the height. So we can combine like terms with these radius, these radii, make it r cubed, because r times r would be r cubed. Keep the pi in there. And then what happens here? This is the number 2, this is 2/3. What's 2 times 2/3? Well, that would be 4/3. So we have our formula for the area of a sphere that you should memorize and learn, 4/3 times pi r cubed. So how does that relate in terms of the cone? Now remember, the cone we had said was 1/3 of the area, so then we could plug that in. 1/3 r squared times height times height. So would that be enough information? I forgot the pi r squared times height. And we look down here to the official formula, 1/3 pi r squared times height. And that is all you need to do for the cone. So in problem 4.4, it's asking you in A, 1, 2, 3, and 4. We pretty much have done A, 1, 2. 3 asks you to do it in terms of the diameter. 4 is asking you in terms of the radius, which is what we really want to know. So again, make sure that you know these two formulas: 1/3 pi r squared times height for the cone, 4/3 pi r cubed for the sphere. So you can put that in for A4 on your Moodle course today. B, C, and D are all problems you can do. You do not need to have done the experiment to do these. So you'll need to complete those questions on Moodle. Make sure you hit submit all and finish when you're done. And then the homework for tonight is 10 through 21. And you should complete that in your notebook or online if that's how you're doing it. And we will correct that tomorrow. We will complete lesson 4.5, which is very short, and begin the review. Remember that we will review Wednesday and Thursday. We'll review and take some vocab and multiple choice quiz, and the final exam for this unit will be on Friday. Thanks again, and I hope you enjoy your day.